Okay, so we watched another 5 minutes of Jacob Lurie's talk, and it gets fairly abstract pretty quickly, but what were some of the things he was trying to point out?
Well, he said that number systems were ubiquitous.
Yeah, we learned a new word, ubiquitous. What does it mean?
It means widely used.
Okay, or that number systems appear sort of everywhere in math.
So there's a lot of them.
Okay. Interesting.
Yeah.
What were some questions that he said math cannot answer?
Well, I think he was talking about like a new set, just a set of numbers are these elements of R real, or are we imagining them?
Aha, yeah, so like a kind of a philosophical question. Are numbers real? Not the definition of real numbers, but do they actually exist?
Or do we just imagine them?
What do you think? Do you think numbers are real, or do you think we've just made them up?
Well, sort of both.
Oh, both. Interesting.
Probably some numbers certainly don't exist. Like,
what do you think? What's a number that doesn't exist?
well, like I, maybe.
Oh, you don't think I exists? Okay.
You can't have
I-
a quantity I of something.
Interesting. What do you think? Do you think numbers exist, or do you think we just made them up?
I think for the most part, they exist.
Okay. Do you think I, for example?
Well, it doesn't exist. Like you can't have you can't have I of something. You can't say something is in I days from now.
Okay.
In that context, it wouldn't make any sense.
All right. Well, that's neat. So I want to show you one other thing that he was talking about and connect it with the 4n plus 1 primes.
Right.
So what's an example of a prime of the form 4n plus 1?
13.
13. Okay. So he said if you look at the integers, you have unique factorization. 6 equals 2 times 3. 12 equals 2 times 2 times 3.
Yeah.
You have unique factorization.
Yeah.
But if I go to a higher number system, and since you guys were just talking about I, it actually helps. If I look at numbers of the form a plus bi, where a and b are integers, all of a sudden I lose unique factorization. In some cases. Okay. So 13 is an interesting example. How does 13 factor in the integers?
It's just 13 and 1.
times 1.
13 times 1. So you think, there you go.
Yeah.
I have to be careful. I said you lose unique factorization. That's actually not what I meant. Here there's still unique factorization. It's just that 13 isn't prime anymore. 13 factors into 3 plus 2i times 3 minus 2i. So let's multiply that out. 3 times 3 is
9.
9. 3 times minus 2i is
Minus 6i.
2i times 3 is
Plus 6i.
And
And then plus 4. Or
2i times minus 2i.
it would be minus 4 times minus 1. So plus 4.
So 9 plus 4 is
13.
So all of a sudden 13 factored.
is it prime?
So all of a sudden 13's not prime anymore.
Interesting.
But you probably will have some new primes.
Yeah. For example, I just showed you a new prime
3
number.
3 plus 2i.
3 plus 2i.
And 3 minus 2i, I guess.
Yeah. And those primes are related to each other.
Yeah.
So it's interesting. So as you go up, sort of some of your properties that you had before kind of disappear if 13's not prime anymore in the complex integers. When it used to be prime in just the plain old ordinary integers. So one of the reasons I wanted to talk about this today is when we were coming home last night in the car, you were mentioning in school you're learning about rational numbers and real numbers and whole numbers and things like that.
Yeah.
And I wanted to kind of show you that even sort of university professor mathematicians, when they're talking about math, they talk about this kind of stuff and why it's important. And here are some examples today of why knowing this is important. Alright?
Right.
Yeah.
Alright, good work today, guys.